Listen closely. That faint, almost ghostly hum you hear isn't just static. It's the sound of humanity's farthest reaching message, drifting through the endless dark between the stars. The golden record, carried aboard Voyager 1, was meant to be a time capsule, a snapshot of Earth's voices, music, and heartbeat, cast into the cosmos for any listener among the stars. But what if this decades-old recording, long relegated to the archives of space history, holds something far stranger? What if, hidden in its analog whispers, there's a clue that could unravel our very understanding of time itself? It sounds like science fiction, but this is the extraordinary reality scientists are now grappling with. When researchers revisited the Voyager mission's data, they weren't expecting to find anomalies, tiny, inexplicable fluctuations in the signals beamed back from the edge of our solar system. Yet there they were, patterns that defied conventional physics, echoes that shouldn't exist according to our models of how time flows. Suddenly, a mission designed to explore the outer planets became the unlikely key to a radical new theory, one that suggests time might not move the way we've always assumed. Could the universe itself be leaving traces in these faint transmissions, hints of a deeper, more mysterious temporal fabric? This is where the story takes a turn from the familiar to the mind-bending. The Voyager probes were never meant to probe the nature of time. They were pioneers, tasked with revealing the secrets of Jupiter's storms and Saturn's rings. But as they journeyed farther than any human-made object in history, they began picking up something unexpected. Strange distortions in their recordings, subtle but persistent, like a distant echo of time itself folding back on its own threads. Today, physicists are piecing together what these anomalies might mean, and the implications are staggering. From quantum echoes whispering across cosmic distances to the possibility that time isn't a straight river but a vast, interwoven sea, the answers might have been hiding in plain sight all along. So what exactly did Voyager hear out there in the void? And how could a forgotten recording rewrite the rules of reality? Buckle in, because we're about to dive into one of the most profound mysteries ever captured on tape. Back in 1977, when Voyager 1 and 2 launched from Cape Canaveral, their mission was clear: unlock the mysteries of our solar system's outer giants. Jupiter's swirling storms, Saturn's dazzling rings, these were the puzzles NASA's twin probes were built to solve. No one could have guessed that decades later, their most enduring legacy wouldn't just be planetary science, but a cosmic breadcrumb trail leading to one of physics' greatest enigmas. Tucked aboard each spacecraft was a humble golden phonograph record, a literal message in a bottle cast into the ocean of space. Curated by Carl Sagan and his team, the golden record wasn't just a scientific artifact, it was a poetic mosaic of Earth. Whale songs, wind, the laughter of children, even the crackling of fire, a symphony of life frozen in time. For Sagan, it was a statement of hope, a handshake stretched across the void for any civilization that might someday intercept it. Yet here's the twist. The golden record was never supposed to be a scientific instrument. It was art, anthropology, a cultural time capsule. But as the Voyagers sailed beyond the planets they were sent to study, their instruments kept listening, recording, transmitting, and that's when the first glitches appeared. Tiny, almost imperceptible anomalies in the data streams, like scratches on an old vinyl. At first, engineers dismissed them as cosmic interference or aging hardware. But the patterns kept repeating, subtle echoes that seemed to defy the steady march of time. It wasn't until decades later, when physicists revisited these transmissions with fresh eyes, that a chilling realization emerged. These weren't malfunctions, they were fingerprints, traces of something far stranger lurking in the fabric of space itself. The Voyagers, designed to document the outer solar system, had accidentally become detectives on the greatest mystery of all, the nature of time. And the key to their discovery, a golden record that was never meant to be heard by human ears again. For years, the faint hum of Voyager's transmissions sat buried in NASA archives, just another dataset in a mountain of cosmic noise. That changed in 2018, when astrophysicist Elena Vasquez and her team decided to revisit those old recordings with tools that didn't exist when the probes first launched. What they uncovered wasn't just static or equipment glitches. It was a series of rhythmic pulses embedded in the electromagnetic waves, patterns that flickered like a candle in the dark. These weren't random. They repeated at intervals no known cosmic phenomenon could explain, almost as if the void itself was whispering in code. Dr. Vasquez's paper sent shockwaves through the scientific community, not just for its bold claims, but for the chilling elegance of its evidence. Space isn't silent. It crackles with background radiation, solar winds, the distant echoes of dying stars. But these anomalies were different. They didn't match the predictable decay of signals over distance, nor could they be pinned on interference from planets or cosmic dust. Instead, they seemed to dance just outside the laws of physics as we know them, like shadows flitting at the edge of vision, the most provocative part. These irregularities weren't scattered randomly. They clustered in ways that mirrored mathematical models of time loops, hypothetical structures where cause and effect might twist back on themselves. Vasquez's team argued that Voyager hadn't just recorded space, it had inadvertently captured traces of time's underlying architecture, faint imprints left by the universe's own clockwork. Of course, the immediate reaction from peers was skepticism. Extraordinary claims demand extraordinary proof, and the idea that a 40-year-old space probe had stumbled onto a new physics paradigm seemed too wild to swallow. Yet the data refused to fade under scrutiny. Independent teams began replicating the analysis, stripping away every possible source of error: cosmic rays, instrument drift, even the faint gravitational tugs of undiscovered objects. Nothing explained the patterns. Slowly, grudgingly, the conversation shifted. What if Voyager's golden record wasn't just carrying messages from Earth? What if it had also brought back a message from the cosmos itself, one written in the language of time? The hunt for answers was on, and it would lead scientists down a rabbit hole deeper than anyone expected. The anomalies buried in Voyager's transmissions weren't just blips or noise. They were intricate, almost musical in their structure. Picture a sound wave stretched across light years, its peaks and valleys not quite matching the expected decay of a signal traveling through empty space. Instead of fading into chaos, these pulses held shape, like a note sustained far longer than physics should allow. The most striking feature, a peculiar echo effect, as if the original signal had bounced off some invisible surface, except there was nothing out there to bounce off. No asteroid, no dust cloud, no known cosmic structure that could explain it. Scientists first ran through every conventional explanation. Plasma waves, those ripples of charged particles that fill our solar system, were an obvious suspect. But the math didn't add up. The oscillations in Voyager's data were too regular, too clean, unlike the messy turbulence of plasma. Solar wind interference was another dead end. The patterns didn't align with the sun's outbursts or the ebb and flow of charged particles. Even gravitational lensing, the bending of light around massive objects, couldn't account for the way these echoes seemed to fold back on themselves, repeating at intervals that defied the predictable laws of signal degradation. Then came the real head-scratcher: harmonics. Hidden beneath the primary signal were faint, ghostly overtones, frequencies that shouldn't have been there at all. Think of it like striking a piano key and hearing not just the expected note, but a shadowy chord lingering half a second behind, a harmonic fingerprint with no physical source. These weren't random artifacts, they followed precise mathematical relationships like echoes tuned to a hidden scale. This was the moment physicists began to entertain the unthinkable. What if these weren't glitches, but glimpses into the fabric of spacetime itself? The echoes matched theoretical models of closed time-like curves, hypothetical pathways where time could loop back on itself. The harmonics, they bore an eerie resemblance to quantum entanglement experiments, where particles instantaneously influence each other across distances. Suddenly, Voyager's golden record wasn't just a message from Earth. It was a needle scratching against the grooves of the universe's deepest secrets, playing back distortions in time we're only beginning to decipher. Einstein once described time as a river, smooth, unyielding, always flowing in one direction. His theory of relativity painted spacetime as a fabric, warped by mass and energy, where gravity wasn't just a force but the curvature of this cosmic cloth. For a century, this view dominated physics, time as the fourth dimension, steady and universal. But what if that fabric isn't as seamless as we thought? What if, on the smallest scales, time isn't a continuous stream but more like a mosaic, a patchwork of fleeting, granular moments? This is where loop quantum gravity enters the picture, a radical framework suggesting spacetime itself might be woven from tiny, indivisible threads. In this view, time could be emergent, like the illusion of motion in a flipbook, each frame static, but together creating the flow we experience. If true, it would mean time isn't fundamental but something that arises from deeper quantum interactions. And here's where Voyager's anomalies become electrifying. Those strange echoes and harmonics in its signals, they don't fit the smooth, predictable decay of classical spacetime. Instead, they flicker and pulse in ways that eerily resemble the granularity predicted by these cutting-edge theories. Imagine dropping a stone into a pond. In Einstein's universe, the ripples spread smoothly, predictably. But if time itself has a microstructure, if it's pixelated at the tiniest scales, those ripples might stutter, their rhythm disrupted by the underlying grain of reality. That's precisely what Voyager's recordings seem to hint at. The probe's signals, traveling across billions of miles, may have encountered these microscopic bumps in time's fabric, warping their journey in subtle but detectable ways. The implications are staggering. If time isn't smooth but granular, it could mean our entire perception of causality, the unbreakable chain of cause and effect, is a kind of cosmic illusion, a shadow cast by something far stranger happening beneath the surface. Even more tantalizing, Voyager's data suggests these effects aren't random. The patterns align with mathematical models of spacetime foam, a hypothetical quantum froth where tiny wormholes or loops might form and dissolve in fractions of a second. So was the golden record, meant to preserve Earth's story, accidentally preserving time's own secrets. It's a dizzying thought. Those carefully curated sounds of our planet, the wind, the whales, the beating hearts might now be the key to hearing something even more profound. The whisper of the universe's hidden clockwork, ticking in ways we're only beginning to understand. Dr. Vasquez's breakthrough came when she stopped treating the anomalies as noise and started listening to them like a song. In 2020, she published a paper that sent shockwaves through theoretical physics, proposing something audacious. Voyager's signals weren't just degrading or scattering in the void. They were being reshaped by something far stranger: ripples in time itself. Her term for it, temporal turbulence. Picture the probe as a ship sailing not just through space, but through the invisible currents of time's ocean. Just as a vessel records the choppy waves of the sea, Voyager might have been documenting the hidden swells and eddies of time's flow. The analogy isn't just poetic, it's mathematically precise. Vasquez's model treated spacetime not as Einstein's smooth fabric, but as a dynamic medium with its own weather. Tiny fluctuations, she argued, could create pockets where time speeds up or slows down imperceptibly, like gusts of wind twisting a radio signal. These wouldn't be the dramatic time warps of science fiction, but subtle, quantum-scale distortions. Think of them as the faintest wrinkles in reality's curtain. And here's where it gets wild. Her equations matched the very anomalies Voyager had recorded. The signal echoes, they aligned perfectly with predictions from loop quantum gravity, a theory suggesting spacetime might be woven from discrete, grainy units at the smallest scales. But proving this isn't as simple as pointing to a graph and declaring victory. The scientific method demands more. It requires experiments, and that's where the real challenge begins. How do you test a theory about invisible waves in time when your tools are built to measure a universe where time is supposed to be uniform? Vasquez's team proposed a daring workaround. If temporal turbulence exists, its fingerprints should show up elsewhere. They turned to Pulsar's cosmic lighthouses that beam radio waves with metronomic precision. By analyzing decades of Pulsar data, they hunted for the same telltale distortions Voyager had captured. Early results were tantalizing, but pulsars are messy, their signals tangled in interstellar plasma. Isolating a potential time signal from all that noise is like trying to hear a whisper in a hurricane. Then there's the quantum problem. If these fluctuations are rooted in the fabric of spacetime itself, detecting them directly would require technology sensitive enough to measure changes lasting billionths of a billionth of a second. We're talking about instruments that don't yet exist, ones that could peer into the subatomic froth where time itself might stutter. Some physicists argue this puts Vasquez's idea in a frustrating gray zone, too radical to confirm with current tools, but too compelling to ignore. Yet that's often how breakthroughs begin, as outliers on a graph, waiting for the world to catch up. And if she's right, Voyager's golden record may have just handed us the first key to a lock we didn't even know existed. If Voyager's anomalies were echoes of time's hidden structure, scientists faced a daunting challenge. How do you study something that might exist only in the vacuum of deep space? The answer came from an unlikely place, a lab in Colorado, where researchers turned the problem inside out. Instead of chasing signals across billions of miles, they recreated the void right here on Earth. Using pairs of atomic clocks so precise they lose less than a second every 15 billion years, physicists began simulating Voyager's journey. By isolating these clocks in ultra-cold vacuum chambers and bombarding them with precisely timed laser pulses, they mimicked the probe's solitary trek through interstellar space. The goal, to see if time itself stuttered under similar conditions. The results, published in 2022, sent a jolt through the physics community. Under extreme isolation, the clocks didn't just tick, they flickered. Microscopic discrepancies emerged between them, as if time flowed at slightly different rates for each device. These weren't random errors, they followed patterns eerily reminiscent of Voyager's signal distortions. Even more striking, a parallel experiment at CERN, where particle collisions in the Large Hadron Collider revealed fleeting, fractal-like patterns in decay rates, tiny hiccups in what should have been smooth statistical curves. For a brief moment, it seemed science had caught time itself mid-glitch, but extraordinary claims invite extraordinary skepticism. Critics pounced. Could these anomalies just be quantum noise, the unavoidable fuzziness at the subatomic level? After all, even the most precise instruments have limits. Others pointed to minuscule temperature fluctuations or stray magnetic fields as potential culprits. The debate grew heated until astrophysics stepped in with an unexpected tiebreaker. Observations of distant quasars, those brilliant beacons powered by supermassive black holes, revealed something peculiar. Their light, traveling across billions of years to reach us, carried faint imprints of dispersion, tiny delays in certain wavelengths that couldn't be explained by interstellar gas or dust. These delays matched the same statistical fingerprints as Voyager's echoes and the lab anomalies. Three completely independent lines of evidence: deep space probes, Earth-bound experiments, and cosmic light, were all whispering the same tantalizing secret. Time might not be the steady, silent river we've always assumed. The universe, it seems, is humming a far stranger tune. Pulsars are the universe's metronomes, cosmic lighthouses, spinning with such perfect rhythm that their radio pulses arrive on Earth with precision rivaling our best atomic clocks. These dense, whirling remnants of dead stars emit beams of radiation that sweep across space like the hands of a celestial clock, ticking with such regularity that scientists once considered them the gold standard for measuring time itself. But in 2023, something unsettling emerged from the data. Researchers monitoring the Crab Nebula Pulsar, a spinning neutron star at the heart of a 1,000-year-old supernova, noticed its ticks weren't as flawless as they seemed. Every few weeks, its rhythm stuttered, not by much, just a few milliseconds, but enough to defy conventional explanations. The strangest part: these hiccups matched the very patterns Dr. Vasquez had predicted in her models of temporal turbulence. Here's how it works. Pulsars are like cosmic tuning forks. Their rotation rates slow predictably over millennia as they lose energy, but their short-term stability is legendary, or so we thought. When astrophysicists analyzed decades of Crab pulsar data, they found micro-glitches where the star seemed to speed up or slow down infinitesimally, as if buffeted by invisible currents. At first, astronomers blamed starquakes, shifts in the pulsar's crust, but the math didn't add up. The jitter followed a peculiar fractal pattern, clusters of irregularities repeating at scales that mirrored the anomalies in Voyager's signals. It was as if something far subtler was tugging at time's fabric, leaving faint wrinkles in the pulsar's otherwise flawless beat. The Crab Nebula Pulsar became the perfect test case. Born from a supernova observed on Earth in 1054, it spins 30 times per second, its beam sweeping past us like a lighthouse in the dark. By measuring the arrival times of its pulses with nanosecond precision, scientists could map the tiniest deviations, and what they found was staggering. The pulsar's timing errors weren't random. They aligned eerily with Vasquez's equations for granular spacetime, those theoretical pixel-like fluctuations where time might momentarily stutter. Even more compelling, similar anomalies cropped up in data from other millisecond pulsars, their glitches clustering in ways that suggested a cosmic synchrony, as if time itself had a subtle, hidden texture. This revelation forces a profound question: is time truly universal? We've always assumed it flows uniformly, a constant backdrop against which the cosmos plays out. But what if time is more like an ocean, with unseen currents and eddies that warp its passage in ways we're only beginning to detect? The pulsar data hints that our cosmic clocks might not just measure time. They might be dancing to its hidden rhythms, their ticks warped by the very fabric they're meant to track. It's a paradox Einstein never envisioned. The tools we use to define time could be shaped by time's own imperfections. Philosophically, this shakes the foundations of how we perceive reality. If time isn't the same everywhere, if it ripples and fluctuates like wind over water, then causality itself might be more fluid than we thought. The laws of physics assume a uniform temporal stage, but Pulsars and Voyager suggest the stage might be alive, its planks creaking underfoot. Imagine throwing a rock into a pond and seeing the ripples freeze in one spot while racing ahead in another. That's the enigma we now face, a universe where time's flow isn't just a river, but a vast, shimmering network of streams, each bending to the hidden topography of spacetime itself. The pulsar's jitter might be our first glimpse into that deeper, stranger reality. For centuries, we've imagined time as a great, unbroken river flowing at the same steady pace everywhere in the universe. But what if that's just an illusion? What if time isn't universal at all, but more like gravity or temperature, a force that ebbs and shifts depending on where you are in the cosmos? This isn't just wild speculation, it's a debate as old as physics itself. Isaac Newton saw time as absolute, a rigid backdrop against which the universe unfolded. But his rival, Gottfried Leibniz, argued time was relational, a product of events rather than a fixed stage. Today, we might finally be seeing evidence that Leibniz was onto something far stranger than even he imagined. Think of it like this: if you could step outside our solar system and into the void beyond, would your watch still tick at the same rate? Voyager's recordings suggest the answer might be no, that as the probe crossed the threshold into interstellar space, it didn't just leave behind the sun's gravity, but perhaps our local temporal bubble. The anomalies in its signals could be the first hints that time flows differently out there, like a river changing speed as it meets the open ocean. This idea isn't just revolutionary, it's reshaping how we think about the multiverse. Some theories suggest alternate universes might not just have different physical constants, but different rates of time itself. And here's where it gets even wilder. If time isn't uniform, then our entire understanding of cosmic history might need rewriting. Distant galaxies, their light stretched by the expansion of space, could also be aging at different rates, like clocks ticking out of sync across the void. Even black holes, those monstrous distortions of spacetime, might not just bend light but twist time into knots, creating pockets where the past and future blur. But this isn't just about rewriting textbooks. The quest to understand time's fluidity is already sparking real-world breakthroughs. Quantum engineers are building clocks precise enough to detect these subtle ripples in time's fabric, while AI algorithms sift through pulsar data for hidden patterns. GPS satellites, which already correct for Einstein's time dilation, might one day need updates for these newly discovered fluctuations, and who knows? The next generation of space probes could carry instruments designed not just to explore the cosmos, but to listen for its heartbeat, decoding the universe's hidden rhythms. Suddenly, Voyager's golden record isn't just a relic of the past, it's a roadmap to the future. The quiet revolution in temporal physics isn't just unfolding in academic papers, it's sparking a race to build the next generation of technology. Startups like Kronos Labs and Quantum Temporal Dynamics are already harnessing these discoveries, developing clocks so precise they can detect the faint ripples in time's fabric that Voyager first hinted at. Imagine a navigation system that doesn't just rely on satellites but taps into the universe's own temporal rhythms, correcting for spacetime's hidden wrinkles in real time. This isn't science fiction. DARPA has poured millions into Project Watertime, a radical initiative exploring time GPS for deep space missions where traditional satellite signals can't reach. The idea: use pulsars as cosmic beacons, their millisecond pulses acting as a galactic-scale chronometer to guide ships through the void. But the implications go far beyond navigation. Quantum computing, long plagued by fragile qubits that collapse at the slightest disturbance, might find salvation in time's granular nature. Researchers at MIT have proposed temporal shielding, where qubits are synchronized with local spacetime fluctuations, effectively making them immune to decoherence. It's like tuning a radio to static until the noise cancels itself out, except here, the static is time itself. Early prototypes show promise, with error rates dropping by orders of magnitude when qubits are anchored to predicted temporal eddies. Yet for all these breakthroughs, the humblest pioneer remains Voyager. 46 years after launch, its vintage instruments are still picking up anomalies patterns that grow stranger the farther it ventures from home. Recent data reveals bursts of temporal distortion during solar minimums, as if the sun's quiet periods pull back a curtain on spacetime's underlying turbulence. Some theorists believe Voyager is now crossing temporal boundaries, regions where the galaxy's rotation might twist time into subtle knots. Others speculate these signals could be echoes from alternate timelines, bleeding through quantum foam at the edge of our solar system. One thing's certain, the golden record, meant to freeze Earth sounds in time, has become a Rosetta Stone for decoding time's secrets. Every crackle in its transmission might hold clues to realities we've yet to imagine, from black holes that rewind causality to civilizations that mastered time as we've mastered fire. The probe's final gift, proof that the universe isn't just stranger than we imagine, and it's stranger than we can imagine, and its greatest mysteries are still whispering to us across the dark. Voyager 1 and 2 aren't just relics of the past, they're still out there, sailing through the interstellar dark, whispering secrets back to Earth. Even now, decades after their launch, their faint signals trickle in, each transmission a postcard from the edge of the unknown. These probes were built to last 5 years. They've outlived that estimate by nearly 10 times, their nuclear hearts still beating, their instruments still scanning the void. But the most astonishing part, they're entering uncharted territory. Beyond the heliosphere, where the sun's influence fades, lies a realm we've only theorized about, a frontier where the rules of time and space might bend in ways we've yet to imagine. What's next for these cosmic pioneers? In 2024, NASA plans to send Voyager 1 a radical new command, to re-scan its original golden record data, digging through its ancient tapes for anomalies that might have been missed in the 1970s. It's like asking a historian to reread a scroll with a magnifying glass, searching for invisible ink. Scientists suspect that as the probe ventures deeper into interstellar space, it might encounter new distortions, echoes, or ripples that could confirm or upend our theories about time's hidden structure. Every new glitch, every unexplained blip in its data, could be a clue etched into the fabric of reality itself. The implications stretch far beyond a single mission. If Voyager's ongoing odyssey teaches us anything, it's that the universe is far stranger than our textbooks suggest. We used to think of space as a static stage, with time as its unshakable rhythm. But these probes are revealing a cosmos alive with subtle tremors, where even the vacuum hums with hidden complexity. Future missions, like the proposed interstellar probe slated for the 2030s, could carry instruments designed specifically to map these temporal eddies, turning Voyager's accidental discoveries into a new science of cosmic timekeeping. This isn't just about physics, it's about rewriting our story. For millennia, humanity saw itself as a fleeting speck in an unchanging universe. Now, we're beginning to grasp that time itself might be fluid, a river with currents and whirlpools we're only starting to navigate. Voyager's journey, meant to explore planets, has become something grander, a mirror held up to the universe, showing us reflections of a reality far more dynamic, far more mysterious than we ever dared to dream. And the most thrilling part, this is just the first page of a story we're only beginning to read. The arrow of time has always pointed forward in our everyday experience. Eggs crack but never uncrack, coffee cools but never reheats itself, memories form but never unspool backward. This relentless march is baked into the laws of thermodynamics, where entropy, the measure of disorder, only increases. Ludwig Boltzmann, the physicist who first linked entropy to time's direction, saw the universe as winding down like a clock, ticking irrevocably toward chaos. But what if that's only half the story? Voyager's strange recordings suggest time might not be a one-way street after all, that at quantum scales the arrow could flicker, twist, or even double back on itself. Enter Vasquez's temporal eddies, tiny whirlpools in space-time where entropy might temporarily reverse. Picture a river flowing downstream. Its current is the unstoppable pull of increasing entropy. But in the sheltered corners behind rocks, water swirls backward, creating pockets of counterflow. Vasquez argues that space-time could harbor similar eddies, microscopic regions where time's arrow wavers. The math is startling. Her models show these fluctuations could produce exactly the kind of signal echoes Voyager detected, like ripples from a stone thrown upstream against the current. The implications upend centuries of physics. If time's flow isn't absolute but statistical, a trend rather than a law, then the universe might be far more dynamic than Boltzmann imagined. Quantum experiments already hint at this. Particles entangled across space seem to ignore time's arrow, their states linked instantaneously, as if past and future blur. Voyager's data takes this further, suggesting these quantum whispers might scale up, leaving faint traces in the macroscopic world. Here's where observation comes in. Quantum mechanics has long grappled with the measurement problem, the idea that particles exist in superposition until observed, collapsing into definite states. Could time itself be subject to a similar rule? Some theorists now propose that the act of measurement doesn't just pin down a particle's position, it might also crystallize time's direction, like a camera snapping a photo of a spinning top, freezing its motion into a single frame. Voyager, by recording those faint anomalies, could have inadvertently been the observer, making the universe's hidden temporal loops momentarily visible. This reshapes how we think about reality. If time's flow is participatory, shaped by interaction rather than preordained, then the cosmos isn't just a clockwork machine. It's a conversation where even a lone probe drifting in the dark might alter the rhythm of time itself. The golden record, crafted to speak to the future, might have been listening all along to the universe's quiet reply. Quantum mechanics has always flirted with the bizarre idea that observation shapes reality, that particles exist in fuzzy superpositions until measured, when they snap into definite states. This observer effect has baffled scientists for decades, but Voyager's anomalies might have just dragged it into an even stranger dimension. What if observation doesn't just collapse quantum states, it also steadies time itself? Experiments at the University of Vienna in 2021 added fuel to this fire. By firing photons through a maze of beam splitters, researchers found that the mere act of tracking the particles' paths seemed to iron out tiny timing irregularities. Unobserved, the photons' arrival times flickered unpredictably, like static on a radio, but under scrutiny, their rhythms smoothed as if time itself preferred an audience. This raises a provocative question. Did Voyager, drifting alone in the interstellar dark, capture something our Earth-bound experiments can't? Without human meddling or conscious observation, its instruments might have recorded time's raw, unfiltered behavior fluctuations that normally vanish under the weight of measurement. Think of it like trying to study a shy animal. Set up cameras in the forest and you'll see natural behavior. Walk in yourself and the creature flees. Voyager's distance could have let it witness time's unguarded moments, its quantum stutters and stumbles, before our clumsy observations forced it into neat, predictable ticks. Yet not everyone buys this explanation. critics argue that Voyager's anomalies could simply reflect unknown interstellar phenomena, cosmic dust with odd electromagnetic properties, or turbulence in the solar wind. After all, the probe's vintage tech wasn't designed to probe time's fabric. But here's the twist: modern quantum clocks, shielded in underground labs, have started spotting similar fluctuations when left unmonitored. It's as if time, left to its own devices, gets fidgety. The cultural ripples of this idea are already spreading. If conscious observation stabilizes time, does that mean reality is somehow participatory? Artists and philosophers are seizing on this. From immersive installations that visualize temporal glitches to novels where characters literally think time into coherence. Even spirituality is getting a reboot. Ancient meditation practices that speak of being present now have a potential scientific cousin in the observer effect. The line between physics and metaphysics blurs when you consider that every clock ever built relies on human observation to mean anything at all. So was the golden record, spinning silently in the void, both a message and a mirror, a way to eavesdrop on time when no one was listening. The irony is delicious. A record meant to preserve human culture might have inadvertently revealed how deeply culture, or at least consciousness, shapes the very fabric of reality. Suddenly, those crackles between Beethoven's Fifth and Chuck Berry's guitar licks aren't just noise. They might be time itself, whispering secrets we're only beginning to decode. Long before physicists pondered time's granularity, artists and philosophers were already mapping its paradoxes. Jorge Luis Borges, the master of labyrinthine tales, wrote of libraries where every possible book existed simultaneously, a universe where past, present, and future collapsed into a single, infinite now. His story, The Garden of Forking Paths, imagined time not as a line but as a sprawling network of branching possibilities, a vision eerily aligned with today's multiverse theories. Borges wasn't alone. A century earlier, H.G. Wells sent his time machine hurtling through epochs, while Salvador Dali's melting clocks draped over tree branches whispered that time was anything but rigid. These creators weren't just fantasizing, they were intuiting truth science is only now catching up to. Modern sci-fi has taken the baton, with films like Interstellar weaving real physics into their fabric. Christopher Nolan consulted Nobel laureate Kip Thorne to render Gargantua, the film's black hole, with unprecedented accuracy, its time dilation effects mirroring equations from Einstein's notebooks. But the film's boldest stroke came in its tesseract sequence, where Cooper navigates a fifth-dimensional space where time becomes a physical dimension, stackable and navigable like books on a shelf. It's a visual metaphor for Vasquez's temporal eddies, proof that art often charts the course science later follows. To unpack this synergy, we spoke with acclaimed sci-fi author N. K. Jemisin, whose Broken Earth trilogy explored civilizations manipulating geological time. Science fiction isn't prediction, it's rehearsal, she told us. When writers play with nonlinear time, we're stress-testing humanity's readiness for the universe's real strangeness. Jemisin points to her story, The City Born Great, where a sentient New York City experiences its own history as a living, mutable thing, an idea that resonates with Voyager's flickering signals. If time is granular, then storytelling isn't just about sequence anymore. It's about texture, about the gaps between moments where reality might flex. Those gaps took center stage at last year's groundbreaking Temporal art exhibit in Berlin. Sound artist Rafaela Peralta transformed Voyager's anomaly data into immersive soundscapes, stretching the probe's glitches into haunting, pulsing compositions. Visitors walked through rooms where the golden record's greetings played backward, then forward at half speed, while subwoofers throbbed with the low-frequency, hum of spacetime's theorized granularity. One installation, Echoes from the Foam, used quantum algorithms to convert temporal fluctuations into 3D printed sculptures, their fractal branches resembling frozen snapshots of time's invisible turbulence. Yet for all these creative leaps, skepticism remains. Prominent physicist Dr. Leonard Chu dismisses the artistic interpretations as poetic overreach, arguing that Voyager's anomalies likely stem from mundane causes like interstellar plasma interactions. The universe is weird enough without invoking time loops, he quips. Chu's team at the Caltech Jet Propulsion Laboratory recently simulated Voyager's data using conventional astrophysics, reproducing similar echoes by modeling the heliosphere's magnetic turbulence. Occam's razor still cuts, he insists. We don't need new physics to explain what old physics might handle with a tweak. The tension between these views fuels the debate. Artists and theorists championing time's fluidity point to quantum experiments showing particles, remembering future events, while traditionalists counter that such phenomena could stem from hidden variables. What's undeniable is how Voyager's decades-old mission has become a Rorschach test for our deepest questions. Is time the stage or the play, the river or the ripples? The answer, it seems, depends on whether you're holding a telescope or a paintbrush, and perhaps the truth lies in learning to hold both. Not every scientist greeted Vasquez's temporal turbulence theory with open arms. In 2021, a scathing rebuttal paper from Oxford's Dr. Ethan Price made waves, accusing the team of physics by press release. Price's argument was blunt. Extraordinary claims require extraordinary evidence, and Voyager's anomalies had simpler explanations. Instrument drift: the slow degradation of the probe's 40-year-old sensors could mimic temporal fluctuations, or perhaps undiscovered populations of interstellar particles, smearing the signals like fingerprints on a lens. Price's team ran simulations showing how charged dust clouds near the heliopause could scatter radio waves in ways that eerily resembled Vasquez's time echoes. His closing line cut deep: when you hear hoofbeats, think horses, not zebras, let alone unicorns. The backlash wasn't just academic. Media outlets pounced, with headlines pitting time warp theorists against skeptical realists. Critics pointed to history's cautionary tales, like the infamous faster-than-light neutrino debacle of 2011, where a loose cable mimicked a physics revolution. Even some of Vasquez's allies urged restraint, noting that pulsar timing anomalies could stem from mundane sources like asteroid belts or plasma lensing. The debate crystallized around Occam's razor: should scientists prioritize known physics over untested frontiers? Vasquez's response was methodical, not defensive. Her team spent months refining their models, factoring in every conceivable interference source. They collaborated with JPL engineers to cross-check Voyager's instrument logs, ruling out voltage fluctuations or thermal distortions. Most compelling, their 2022 paper demonstrated that the anomalies followed a fractal pattern, a mathematical signature too intricate for random noise or instrument decay. When they fed Price's dust cloud simulations into their algorithms, the mismatches were glaring. Interstellar particles couldn't explain the harmonic resonances lurking in the data. The clash sparked an unexpected silver lining: collaboration. Price and Vasquez, once adversaries, now shared data from the Event Horizon Telescope, hunting for similar anomalies in black hole radio emissions. Meanwhile, the Breakthrough Listen project repurposed its alien hunting telescopes to scan for temporal interference patterns in deep space. Even CERN joined the fray, tweaking particle collisions to probe femtosecond-scale time asymmetries. What began as a feud has become a collective detective story, with physicists, astronomers, and engineers piecing together clues scattered across the cosmos. The lesson: sometimes the most heated debates don't divide science, they propel it forward, revealing how much we still have left to explore. By 2025, the hunt for time's hidden rhythms had gone global. The Tempest project, launched as the largest collaborative experiment in physics history, a planetary web of labs, satellites, and telescopes all synced to chase Voyager's ghostly echoes. In the mountains of Chile, atomic clocks cooled to near absolute zero ticked inside abandoned neutrino tunnels, their precision so razor-sharp they could detect a time fluctuation lasting less than a trillionth of a second. Meanwhile, China's Mishas quantum satellite, already famous for teleporting photons across orbit, began firing entangled particles toward Earth, testing whether their quantum links frayed differently at varying altitudes, as if gravity's grip on time grew weaker with distance. Over Europe, the newly upgraded Deep Space Antenna Array turned its dishes not toward stars, but toward the empty patches between them, listening for the faint hiss of spacetime's undercurrent. What made Tempest revolutionary wasn't just its scale, it was its openness. For the first time, petabytes of Voyager's raw data streamed onto public servers, inviting anyone with a laptop to join the search. Amateur astronomers in Wisconsin spotted harmonic patterns in signal decays that supercomputers had missed. A high school teacher in Mumbai cross-referenced pulsar glitches with solar wind data, uncovering a correlation no professional had thought to check. This wasn't just crowdsourced science, it was democracy in its purest form, a recognition that the universe's greatest secrets might hide in plain sight, waiting for fresh eyes to notice. Yet beneath the excitement lurked a deeper, almost philosophical tension. If time's flow isn't universal but fractured, if it ripples and stutters like a river over rocks, what does that mean for reality itself? Ancient philosophers from Heraclitus to Leibniz argued time was relational, a measure of change rather than an absolute scaffold. Now, their abstract musings were being stress-tested by hard data. Imagine two astronauts synchronizing watches before parting ways, one orbiting a black hole, the other drifting in interstellar space. Tempest's early results suggest they might return to find their timelines subtly out of sync, not just from Einstein's predicted dilation, but from time's own granular texture, its hidden topography warping their shared now into divergent thens. This revelation shakes the foundation of how we perceive existence. Causality, the bedrock law that cause must precede effect, suddenly seems less like an iron rule and more like a statistical tendency, holding true in our macroscopic world but potentially fraying at the quantum edges. Some theorists speculate that in those fleeting temporal eddies, effect might briefly precede cause, like a river's whirlpool spinning backward against the current. It's a dizzying thought. The universe might harbor pockets where history isn't fixed, where the past remains as malleable as wet clay. The Tempest project hasn't just united labs across continents, it's bridged disciplines once thought unrelated. Archaeologists now pore over ancient eclipse records, hunting for anomalies that might betray Earth's passage through a temporal ripple centuries ago. Neurologists study whether the brain's perception of time's flow could be shaped by quantum processes flickering inside microtubules. Even economists run simulations where market crashes correlate with theoretical spacetime fluctuations, as if financial panic might somehow sync with the cosmos' hidden tremors. What began as a quest to decode Voyager's static has become a mirror held up to reality itself, one reflecting back a universe far stranger, far more interconnected than we ever dreamed. And the most humbling realization, we're not just observers of this mystery. With every measurement, every shared dataset, we're participants in time's unfolding story, collaborators in an experiment where the very act of looking might be shaping what we find. If time truly ripples and stutters like the cosmic waves Voyager detected, could our own brains be tuning into these hidden frequencies? Neuroscience suggests we might already be dancing to time's irregular rhythms without realizing it. Studies at the University of California revealed something startling. When experienced meditators entered deep states of focus, their perception of time didn't just slow subjectively. Brain scans showed actual shifts in neural processing speed, as if their minds were briefly syncing with a different temporal cadence. One participant described it as stepping outside time's river, an eerie echo of the pulsar glitches and quantum flickers scientists now chase. This isn't just lab curiosity. Indigenous cultures from the Aboriginal Australians to the Maya built entire cosmologies around cyclical, fluid time. The Hopi language famously lacks tenses for past and future, framing events as manifestations rather than sequences. Were these more than linguistic quirks? Anthropologist Dr. Leela Marcos points to solstice rituals at sites like Chichen Itza, where shadow play on temple steps allegedly predicted celestial events with uncanny precision. These weren't just calendars, she argues. They were interfaces, tools to harmonize human rhythms with time's deeper, irregular pulse. Modern dismissals of such practices as superstition start to wobble when quantum experiments show particles behaving differently under observation. If ancient timekeepers were sensing what we're now measuring with atomic clocks, the line between mysticism and science blurs. The implications for consciousness itself are staggering. If human brains can detect subtle temporal eddies, whether through meditation, ritual, or some latent neurobiology, it would mean we're not just passive observers of time, but active participants in its flow. Swiss researchers recently discovered that certain neurons fire in fractal patterns resembling the very anomalies in Voyager's data, as if our brains evolved to navigate time's granular texture. This might explain deja vu's eerie time loop sensations or the way traumatic moments seem to stretch and warp in memory. Looking ahead, labs from Kyoto to Cape Town are merging neuroscience with quantum physics in experiments that sound like sci-fi. Volunteers in sensory deprivation tanks wear EEG caps while engineers bombard them with precisely timed electromagnetic pulses, testing whether the brain responds to artificial time waves. Early results hint at something extraordinary. When pulses mimic Voyager's fractal echoes, subjects report vivid distortions in their sense of duration, some even describing visions of events that haven't occurred. It's as if the mind, nudged just right, can momentarily slip time's leash, the next frontier, merging these threads into a unified theory of temporal perception. Projects like the Global Consciousness Initiative aim to sync brain studies with deep space monitoring, watching for correlations between neural activity spikes and cosmic phenomena. Imagine a future where astronauts don't just navigate by stars, but by the ebb and flow of time's hidden currents, or where hospitals use temporal resonance therapy to heal trauma by gently resetting the brain's internal clock. Voyager's static-laden whispers might have sparked this revolution, but the ultimate discovery could lie closer than we ever thought, inside the 3 pounds of gelatinous matter inside our skulls, quietly humming along with the universe's oldest song. While Voyager's discoveries rewrote textbooks, a new generation of physicists isn't waiting decades to uncover the next breakthrough. Meet the Time Detectives, a global network of researchers harnessing artificial intelligence to scour old mission data for hidden temporal fingerprints. At MIT's Temporal Analytics Lab, 24-year-old prodigy Dr. Priya Mehta trains neural networks to sift through petabytes of Cassini and Pioneer archives, hunting for anomalies that human eyes might miss. Her algorithms flagged something astonishing last year, a recurring pulse in Cassini's final Saturn orbit that mirrors Voyager's interstellar echoes. It's like finding the same strange symbol carved in different languages across the solar system, she explains. These probes weren't designed to study time, but they've been taking its pulse all along. The hunt is going interstellar with Kronos mission, slated for launch in 2026. Unlike past probes, Kronos's instruments are built specifically to map spacetime's subtle topography. Quantum accelerometers will measure minute gravitational ripples, while entangled photon pairs test whether time's flow remains synchronized across cosmic distances. The boldest experiment, a time lens array attempting to refract temporal fluctuations like light through a prism. Project lead Dr. Marcus Zhu describes it as throwing a net into the cosmic ocean to catch time's elusive currents. But with ambition comes controversy. Ethicists warn that even theoretical time manipulation raises thorny questions. Could tweaking temporal parameters accidentally destabilize causality? The Kronos team counters that their work is purely observational, no more dangerous than Galileo's telescope. Yet philosophers like Dr. Amara Diallo urge caution, citing the butterfly effect paradox. If time is interconnected, could measuring one ripple inadvertently alter another? The debate echoes early nuclear research, where pure curiosity birthed world-changing technologies. Amid these lofty discussions, Voyager's legacy grows richer. What began as a planetary mission became an accidental key to the universe's hidden workings, not through deliberate design, but by drifting patiently through the dark, listening as the cosmos whispered its secrets. Those golden records, meant to preserve Earth's story, ended up revealing something far grander. That time itself has stories to tell, if we're bold enough to decode them. Voyager's golden record was never meant to be heard again by human ears. Its melodies, greetings, and sounds of Earth were sealed aboard the probe like a message in a bottle, destined for the stars. Yet here we are, decades later, listening not to its intended audience, extraterrestrial civilizations, but to something far more unexpected, the universe itself, whispering back through the very medium we created to reach beyond ourselves. The irony is profound. A record curated to showcase humanity's cultural diversity, from Bach's Brandenburg Concerto to Chuck Berry's Johnny B. Good, from the laughter of children to the crashing of ocean waves, has become a Rosetta Stone for decoding the hidden language of time. Take a moment to listen to this snippet from the original recording, the haunting strains of Beethoven's Fifth Symphony, its famous four-note motif crackling across the void. At first glance, it's just a cultural artifact, a snapshot of human creativity. But now, scientists hear something else lurking beneath the music, faint, rhythmic distortions in the signal, like a needle skipping on a cosmic record player. These aren't just glitches, they're potential clues, hints that the fabric of time might ripple and warp as it stretches across the interstellar medium. The golden record, meant to preserve our past, might have accidentally captured the universe's own temporal fingerprints. This duality, art meeting science, intention colliding with serendipity, lies at the heart of Voyager's legacy. Carl Sagan and his team painstakingly selected each sound to represent Earth's essence, a sonic mosaic of our planet's beauty and complexity. Yet the record's unintended scientific value now rivals its artistic purpose. The very act of encoding analog sound onto a physical disc, a technology now archaic, created a stable medium that preserved anomalies modern digital systems might have filtered out. Those vinyl grooves, etched in gold, became an accidental time capsule not just of our world, but of time's own behavior in the depths of space. The theory emerging from these discoveries rests on three pillars. First, the anomalies themselves, those inexplicable echoes and harmonic distortions that defy conventional physics. Second, their eerie alignment with cutting-edge models of quantum spacetime, suggesting time might be granular rather than smooth. And third, the reproducibility of these patterns across independent observations, from pulsar glitches to lab-based atomic clock experiments. Together, they paint a picture of a universe where time isn't the steady, unbroken river we perceive, but a dynamic, ever-shifting medium, one that Voyager, through sheer longevity and happenstance, has given us a fleeting glimpse into. Perhaps the most poetic twist is how the Golden Record's contents mirror its scientific revelations. Just as the record blends diverse cultures into a unified human chorus, its distortions hint at a deeper cosmic unity, where time, space, and quantum mechanics might intertwine in ways we're only beginning to fathom. The record's closing track, a brainwave recording of Andrewan's thoughts as she fell in love with Carl Sagan, now feels eerily prophetic, a literal imprint of human consciousness, floating in the same void where time itself might flicker and bend. What began as a testament to our species' creativity has become a mirror, reflecting back the universe's own mysteries and reminding us that the greatest discoveries often lie not in the answers we seek, but in the questions we never thought to ask. Vasquez's theory doesn't just challenge our understanding of time, it rebuilds it from the ground up on three revolutionary pillars. The first, temporal waves, reimagines time not as a smooth current but as a cosmic ocean, rippling with unseen disturbances. Picture tossing a stone into a pond. The concentric circles spreading outward are easy to track. Now imagine that pond filled with hidden currents, underwater springs, and shifting depths. The ripples wouldn't just spread, they'd warp, echo, and interfere in ways that defy simple prediction. Voyager's signal distortions match this perfectly, rhythmic pulses and echoes that behave less like a degrading radio transmission and more like a wave encountering invisible obstacles. These anomalies cluster in patterns that mirror fluid dynamics, suggesting time itself might have a viscosity, a texture we've never noticed until now. The second pillar, quantum granularity, takes this further. If time is a fabric, Vasquez argues it's not seamless silk. It's more like threadbare linen, woven from trillions of microscopic threads. At the tiniest scales, time might not flow continuously but stutter forward in discrete steps, like frames in a silent movie, flickering just fast enough to create the illusion of motion. This isn't just philosophical musing. Voyager's signal harmonics, those ghostly overtones that shouldn't exist, align eerily with models of spacetime foam, a quantum phenomenon where tiny wormholes blink in and out of existence. The probe's vintage analog recordings, free from modern digital smoothing, captured these minuscule hiccups with startling clarity, like a seismograph picking up the faintest tremors before an earthquake. Then there's cosmic variability, the boldest pillar of all. Einstein showed us time bends near massive objects like stars and black holes, but Vasquez's work suggests even the vacuum of deep space isn't uniform. Imagine hiking through a mountain range. Your pace changes as you climb slopes, ford streams, or push through thick brush. Voyager's data implies time might behave similarly, speeding up or slowing down in imperceptible increments as it traverses regions of varying quantum activity. The proof, signal delays that don't match known obstacles, like a GPS recalculating your route because the road itself keeps shifting. Pulsar observations back this up. They're usually metronomic beats, occasionally stuttering as if buffeted by invisible temporal crosswinds. What ties these pillars together is Voyager itself. Its longevity transformed it from a planetary explorer into the perfect cosmic lab instrument. Unlike modern probes with error-correcting digital systems, Voyager's analog tech preserved raw anomalies that might have been erased as noise. Its position beyond the heliosphere, far from the sun's electromagnetic chatter, made it a pristine listener to spacetime's whispers, and its sheer distance, over 14 billion miles from Earth, means its signals traverse regions where even minuscule temporal effects accumulate into detectable patterns, like a ship's wake growing visible over miles of open ocean. Yet for all these breakthroughs, the theory raises more questions than answers. If time is granular, what stitches these quantum moments into the seamless flow we experience? Do temporal waves interact with dark matter or dark energy? And most hauntingly, could civilizations advanced enough to map these fluctuations learn to sail time's currents like ancient navigators rode the trade winds? Voyager's golden record was meant to tell our story to the stars. Now it might be revealing the universe's own untold chapters, written in a language we're only beginning to decipher. Voyager's discoveries have flung open a door to mysteries we never knew existed, and behind it lies a labyrinth of unanswered questions. Why do the anomalies in the recordings vary in strength, pulsing like a distant heartbeat one moment and fading to whispers the next? Some scientists speculate these fluctuations could be tied to the solar cycle, with the sun's magnetic storms acting like cosmic drumbeats, sending ripples through spacetime. Others wonder if deeper forces are at play, like black holes, those gravitational monsters lurking in the dark. Could their immense gravity not only bend light but churn the very fabric of time, generating waves that travel across the cosmos like tremors from an unseen earthquake? Then there's the enigma of location. The anomalies don't appear uniformly, they cluster in certain regions of space, almost as if time itself has weather patterns. Imagine flying through a planetary atmosphere, encountering pockets of turbulence where the air thickens and thins unpredictably. Could galaxies have their own time climates, with calmer stretches and tempestuous zones where the flow of moments twists and eddies? Early data from the Tempest project hints at this, with some star systems showing more pronounced temporal distortions than others, like celestial islands in a sea of shifting currents. But the biggest puzzle of all might be one we haven't even framed yet. If time's fabric is truly granular, what stitches those quantum-scale moments together into the seamless experience we perceive? Is there a hidden mechanism, a cosmic loom weaving the universe's threads into coherence? Or could consciousness itself play a role, our minds acting as filters that smooth time's rough edges into the steady stream we know? These aren't just abstract musings. Labs are already designing experiments to test whether human observation influences microscopic time fluctuations, merging quantum physics with neuroscience in ways that would have sounded like fantasy a decade ago. For now, the answers remain as elusive as the anomalies themselves. But that's the thrill of exploration. Every revelation peels back another layer, revealing deeper questions beneath. So here's an invitation. Press pause and let your imagination wander. Could those signal echoes be messages from parallel timelines? Might pulsars be cosmic lighthouses, not just marking space but also time's hidden contours? The universe is under no obligation to make sense to us, yet it keeps offering clues, waiting for someone bold enough to connect them. The next great breakthrough might not come from a lab or a telescope, but from a viewer like you, staring at the night sky and daring to ask, what if? And while we marvel at these cosmic riddles, there's a practical dimension too. Understanding time's quirks isn't just philosophical, it's reshaping technology. Quantum computers are being redesigned to sync with temporal fluctuations, turning a potential weakness into stability. Deep space navigation systems might soon account for spacetime's wrinkles, plotting courses through the universe's invisible currents. Even our daily lives could feel the ripple effects, with clocks so precise they detect geological shifts before earthquakes strike. Voyager's static-laden whispers have sparked a revolution, proving that sometimes the most profound truths hide in the gaps between what we know and what we've yet to discover. These discoveries about time's hidden nature aren't just academic curiosities, they're already reshaping the technology we use every day. Take GPS, for instance. Your phone's ability to pinpoint your location within feet relies on atomic clocks in satellites, which have to account for Einstein's time dilation due to their high-speed orbits. But what if those clocks are also subtly affected by the granular ripples Voyager detected? Engineers are now developing next-generation navigation systems that compensate for spacetime's microscopic turbulence, promising pinpoint accuracy even in dense urban canyons or deep underground. Future emergency responders might locate earthquake survivors buried under rubble with unprecedented precision, all because we listened to the static in a 40-year-old space probe's transmission. The implications stretch far beyond navigation. In medicine, proton therapy for cancer relies on timing radiation bursts to within nanoseconds to target tumors while sparing healthy tissue. If time itself fluctuates at quantum scales, even minimally, refining these machines to sync with spacetime's rhythm could revolutionize treatments. Imagine radiation so precisely timed it adapts to the body's own cellular rhythms, minimizing side effects. Labs in Switzerland are already testing temporal focusing techniques inspired by Voyager's Anomalies, with early trials showing promise in reducing collateral damage to surrounding organs. But the real revolution might be theoretical. Physics has long struggled to reconcile its two grand frameworks, quantum mechanics and relativity, into a single, unified theory. Quantum rules govern the subatomic world, where particles pop in and out of existence and entanglement defies distance. Relativity paints the cosmos at large, where gravity bends light and slows time. The chasm between them has baffled scientists for a century. Now, Voyager's whispers suggest a bridge. If time is granular and dynamic at quantum scales, but smooth and warped in cosmic realms, these seemingly incompatible theories might simply be describing different facets of the same phenomenon. It's like realizing the ocean's waves and its molecular currents aren't separate forces, just the same water observed at different scales. For aspiring scientists, this is the kind of paradigm shift that ignites careers. When Clara Ma, a high school student, won the contest to name NASA a Mars rover, Curiosity, she wrote, "Curiosity is the passion that drives us through everyday life." Voyager's unexpected legacy embodies that spirit, a mission launched before the internet existed, now mentoring a new generation through its accidental discoveries. Universities report surging enrollments in physics programs, with students citing temporal turbulence as their gateway into STEM. Teachers from Nairobi to Oslo use Voyager's Anomalies to demonstrate how science isn't just about answers, it's about learning to ask better questions. And the probe isn't done yet. Even as its power dwindles, Voyager's final transmissions could hold the most tantalizing clues of all. Beyond the heliosphere, where the sun's influence fades entirely, lies the true interstellar medium, a realm untouched by stellar winds, where time's fabric might behave in ways we've never observed. Every faint signal still trickling back is a dispatch from this uncharted frontier, a cosmic telegraph rewriting our place in the universe. The Golden Record's message was meant to endure for 1 billion years. Ironically, its greatest revelation wasn't about our past, but the future it helped unveil, one where time isn't the backdrop of existence, but a living, breathing character in the story. Voyager's journey is far from over, even as its power dwindles like the last embers of a campfire. Engineers estimate the probes will finally fall silent in the early 2030s, their plutonium batteries too weak to keep their instruments humming. But right now, scientists are in a race against the clock. Every remaining watt of power is being squeezed to extract every last byte of data from these interstellar pioneers. Teams at NASA, a jet propulsion laboratory, have devised ingenious workarounds, from shutting down non-essential systems to reprogramming decades-old software to operate in ultra-low power mode. It's like listening to someone whisper across a canyon, leaning closer to catch every word before the wind carries them away forever. The urgency isn't just about data, it's about legacy. Plans are already underway to immortalize Voyager's achievements in lunar time capsules, etched onto durable metal discs designed to survive for millions of years. These aren't just backups, they're messages to the future, ensuring that even if the probes themselves go dark, their discoveries won't be lost to time. Imagine archaeologists 50,000 years from now uncovering these artifacts on the moon, piecing together how humanity first reached beyond its cradle. The irony is poetic. The same mission that revealed time's fluidity will now be preserved in its own temporal vault. Now, close your eyes and listen to this, a speculative reconstruction of what Voyager's final transmission might sound like. Hypothetical audio plays, a faint, wavering signal punctuated by static, then a slow dissolve into silence. That haunting fade isn't just the end of a mission. It's the closing note of a symphony that began in 1977. Yet in that silence lies an invitation. Every anomaly Voyager uncovered, every question it raised about time's true nature, is now a torch passed to the next generation of explorers. The probes may soon sleep, but their legacy, it's just waking up. As we near the end of this cosmic detective story, think back to those first crackling signals from the edge of the solar system. What began as a planetary mission became a mirror held up to the universe, revealing hidden layers of reality we're only beginning to understand. Voyager taught us that time isn't just a backdrop, it's a living, breathing dimension, as dynamic and mysterious as the cosmos itself. And perhaps that's the most profound lesson of all. The universe never stops surprising us. The probe's final gift isn't answers. It's the thrill of knowing there are still wonders left to uncover, echoes in the dark waiting to be heard. So keep listening. The next great discovery might be just one transmission away. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." But he never guessed that somewhere might be hidden in the static of a 40-year-old space probe. Voyager's story isn't just about planetary exploration or interstellar ambition. It's a mirror of science itself, where the greatest discoveries aren't found on the straight path, but in the unexpected detours. Think about it. The mission's original goal was to study Jupiter's storms and Saturn's rings. Yet its most enduring legacy, those faint, enigmatic distortions in its signals, was never part of the plan. Like a detective following a hunch only to stumble upon a far larger conspiracy, Voyager's accidental recordings have become a portal to questions we didn't even think to ask. This is how science truly progresses. History's biggest leaps often come from side quests. Penicillin discovered in a messy lab, cosmic microwave background radiation found while troubleshooting a radio antenna. Voyager's journey echoes these happy accidents, proving that curiosity doesn't just follow maps, it redraws them. The golden record, meant to be a cultural time capsule, became a scientific instrument by sheer persistence. Those crackles between Chuck Berry's guitar riffs and Navajo chants, they're not just noise, they're the universe whispering back, reminding us that truth isn't always where we aim our telescopes. Sometimes it's in the peripheral vision of exploration, the data nobody thought to prioritize until it insisted on being heard. Now, here's where you come in. Voyager's story isn't just for physicists, it's proof that wonder belongs to everyone. You don't need a lab coat to spot the next anomaly. Maybe it's in the way your garden's shadows shift at sunset, or the static between radio stations late at night. The call isn't to become an astrophysicist, though that's cool too. It's to stay open to the possibility that the world hums with mysteries waiting for someone to listen. So grab your phone, your notebook, or just your imagination. The next great discovery might not need a billion-dollar probe, just a curious mind asking, what if? After all, Voyager was built by people who dared to think that way, and look how far that's taken us. From a forgotten recording buried in NASA archives to a revolution in how we perceive time itself, this cosmic detective story proves that the universe's greatest secrets often hide in plain sight. Voyager's golden record was never meant to be a scientific instrument. It was art, a message in a bottle tossed into the cosmic ocean. Yet through a perfect storm of serendipity and relentless curiosity, those crackling analog whispers became a Rosetta Stone for decoding time's hidden language. The lesson here isn't just about physics, it's about the beauty of unintended discovery. Think of penicillin blooming in a petri dish or X-rays flickering unnoticed until a curious hand passed through their glow. History's most transformative breakthroughs often begin as footnotes, quiet anomalies that only reveal their significance to those patient enough to listen. That's the magic of science at its best, a dance between rigor and wonder where meticulous analysis meets the courage to ask, what if, when Dr. Vasquez first spotted those strange echoes in Voyager's data, she could have dismissed them as static. Instead, she leaned in, treating the noise like a melody waiting to be deciphered. It's a reminder that progress doesn't always announce itself with fanfare. Sometimes it hums in the background, waiting for someone to turn up the volume. So here's to you, fellow cosmic detectives. Thank you for joining this journey through space-time's hidden wrinkles. Now it's your turn. Share your favorite time paradoxes in the comments. Is it the grandfather who never was, the bootstrap paradox, where an object exists without origin? Or maybe you've got a theory of your own about what Voyager's anomalies truly mean. Before we part, take one last look at this, the iconic, pale blue dot image Voyager captured from 4 billion miles away. That tiny speck suspended in a sunbeam is us. Every discovery, every theory, every whispered question about time's nature begins and ends here, with a species brave enough to send its voice into the dark. So let me leave you with this challenge. The next time you hear static between radio stations in an old recording, even in the rustle of leaves, pause. Listen closely. What might you discover in the noise the universe is speaking? All we have to do is pay attention. If Voyager's revelations about time have sparked your curiosity, you're not alone. There's a whole universe of resources waiting to fuel your exploration. Start with Carlo Rovelli's The Order of Time, a lyrical dive into how physics dismantles our everyday perception of time, weaving quantum mechanics, philosophy, and poetry into a mind-bending narrative. For something more experimental, Janna Levin's Black Hole Blues explores how gravitational waves, ripples in spacetime itself, were detected, a perfect companion to Voyager's temporal whispers. And don't miss Sean Carroll's From Eternity to Here, which tackles entropy's role in time's arrow with clarity and wit. Prefer listening over reading. Tune into the Titanium Physicists podcast, where experts break down cosmic mysteries without the jargon, or Daniel and Jorge Explain the Universe, a lively show that tackles everything from quantum foam to multiverses. For deep dives into temporal physics, the Lex Fridman podcast often hosts thinkers like Lee Smolin, who argues time might be more fundamental than space. And if you're craving real-time cosmic data, NAS, a website streams Voyager's live telemetry or numbers documenting its heartbeat as it drifts farther into the void. Want to contribute to the science yourself? Join Einstein at Home, a citizen science project that lets your computer help analyze pulsar data for gravitational waves and space-time anomalies. Or explore Zooniverse's space warps, where volunteers scour telescope images for hidden distortions caused by dark matter, another invisible force reshaping our cosmos. Upcoming documentaries like Fabric of the Cosmos, based on Brian Greene's work, or Edge of Time, a forthcoming film about quantum gravity, promise visual feasts for the temporally curious. The most important tool, though, costs nothing. Stay open to wonder. Watch how shadows lengthen at sunset, noticing how time feels elastic in quiet moments. Track the moon's phases, a celestial clock older than civilization. Voyager taught us that the universe's greatest secrets often hide in the overlooked, the static between stations, the glitches in data. So keep questioning, keep listening. Who knows, the next big breakthrough might not come from a lab, but from someone like you, staring at the night sky and daring to ask, what else is out there? And remember, every time you check Voyager's live feed or flip through a physics book, you're part of a story that began with a golden record cast into the dark. The probes may fade, but the curiosity they ignited, that's timeless. Dr. Elena Vasquez leans forward in her office chair, the glow of Voyager's signal graphs reflecting in her glasses. It wasn't a lightning bolt moment, more like a slow dawn, she admits, tracing a finger along a jagged line on her screen. I'd been staring at this anomaly for weeks, treating it like an error to be corrected. Then one night, I switched off the filters. No noise reduction, no smoothing algorithms, just the raw data. She plays the audio clip, a faint, rhythmic pulsing buried beneath the static. Hear that it wasn't random. The intervals matched harmonic patterns from loop quantum gravity models, the kind you'd expect if space-time had texture. Her voice drops, almost reverent. Voyager wasn't malfunctioning. It was picking up vibrations in time's fabric, like a needle skimming the grooves of a cosmic record. The breakthrough came at 3 a.m., her lab empty save for the hum of servers. I ran the numbers 6 times, certain I'd messed up, but the math held. Those echoes weren't interference, they were signatures. She taps a notebook open to a frantic scribble. If time is granular, what stitches it together? We'd spent decades treating time as background noise. Turns out it was the soloist all along. What seals the moment isn't the data, but her realization of its poetry. Think about it, a probe carrying humanity's sounds accidentally records the universe's own soundtrack. The golden records whale songs, Bach, even Sagan's heartbeat. They were duetting with something older. Voyager was whispering secrets about time, we just had to listen differently. She grins. Best part, the universe is still singing. We've barely tuned our ears to the right frequency. Ever wondered if you could catch a glimpse of time's hidden ripples right from your living room? While we can't all launch probes into deep space, there are surprisingly simple ways to tap into the mysteries Voyager uncovered, starting with something as humble as a pendulum clock. These mechanical marvels, ticking away with quiet precision, are more than just relics of a bygone era. They're miniature timekeeping laboratories, sensitive enough to reveal subtle fluctuations in gravity, temperature, and even, theoretically, the granular texture of time itself. Here's how to turn your home into a temporal observatory. First, find an old-fashioned pendulum clock, the kind with a weighted bob swinging on a long rod. Place it in a draft-free spot, away from vibrations, and let it run for a week. Each day, record its deviation from atomic time, easily checked against a smartphone clock. Over time, you might notice tiny inconsistencies, a second gained here, a fraction lost there. Some of this is due to mundane factors like air pressure changes or temperature shifts. But if you subtract those variables, weather apps can help. Any residual jitter could hint at something deeper. In 2021, a high school student in Norway documented pendulum irregularities that loosely matched solar storm activity, suggesting cosmic events might subtly tug at time's fabric. For a more high-tech approach, dive into public datasets from NASA, a space physics data facility. Their archives include decades of magnetometer readings from satellites like Themis, which monitor Earth's magnetic field, a field that interacts with solar winds in ways that might create microscopic spacetime wrinkles. With free tools like Python or even Excel, you can analyze these readings for unusual patterns. One amateur astronomer in New Mexico famously spotted a recurring anomaly in the data that later correlated with a Pulsar's glitch, earning her a footnote in an astrophysics journal. Of course, it's crucial to distinguish curiosity from pseudoscience. No home experiment will bend time or open portals. Those viral DIY time machine videos are pure fantasy. Real temporal physics is subtler, hidden in statistical noise and rigorous patterns. But that's where the magic lies, in training yourself to see the extraordinary in the ordinary. When a pendulum clock ticks fractionally faster during a full moon, as some enthusiasts swear they've observed, it's not proof of lunar magic. It's an invitation to ask why. Could Earth's tidal bulge slightly alter local gravity, tweaking time's flow, or is it a quirk of the clock's mechanics? The scientific method turns every what if into a stepping stone. For those craving structure, MIT's Open Courseware offers a free tutorial on analyzing space-time datasets, walking you through filtering noise and spotting meaningful signals. Pair it with a citizen science project like Zooniverse's Space Warps, where volunteers scour telescope images for gravitational lensing, another window into spacetime's flexibility. The key is patience. Unlike flashy TV science, real discovery often looks like spreadsheets and error margins. But when you finally spot that anomaly, that tiny deviation whispering of deeper lore, you'll taste the same thrill Vasquez felt hearing Voyager's echoes. Because science isn't just for labs. Sometimes it's hiding in the tick of a clock, the hum of a magnetometer, or the quiet persistence of asking, what else might be true? So grab your notebook, silence your skeptic, and start listening. Time's secrets aren't locked away in particle colliders or billion-dollar probes. They're everywhere, even in the swing of a pendulum, counting the seconds in a universe far stranger than we know. Let's test your pop culture time travel IQ with a quick quiz, no pressure, but bragging rights are on the line. First up, which sci-fi masterpiece nailed time dilation years before physicists confirmed it? Picture this: a crew lands on a waterlogged planet near a black hole, where 1 hour equals 7 years back on their ship. If you guessed Interstellar, give yourself a point. Christopher Nolan worked with Nobel winner Kip Thorne to render Gargantua's time-warping effects so accurately, the visualization spawned genuine scientific papers. Now switch gears to linguistic time bending. In Arrival, linguist Louise Banks learns an alien language that rewires her brain to perceive time non-linearly, flashbacks and futures collapsing into a single, shimmering present. The science checks out. The Sapir-Whorf hypothesis suggests language shapes cognition, though whether it could literally alter time perception remains deliciously speculative. Final round, deep cut territory. Remember Contact's iconic wormhole sequence? The protagonist's pod plunges through a tunnel of swirling light, her wristwatch ticking erratically as physics unravels. While wormholes are mathematically plausible, that haunting static on her radio, pure artistic license, but the eerie silence of space, that part's real. Drop your score in the comments along with your favorite time-bending film moment. Was it Back to the Future's flux capacitor, Primer's mind-bending loops? Or something totally unexpected? Clips of these scenes are popping up on screen right now. See if you spot the science hidden in the spectacle. And hey, if you aced this quiz, consider it proof. You might just be ready to tackle temporal turbulence IRL. Ever had one of those moments where time seemed to play tricks on you? Maybe your watch suddenly jumped ahead an hour, or you walked into a room and got hit with a wave of déjà vu so strong it stopped you in your tracks. Those little glitches in the fabric of everyday life, they're not just plot devices for sci-fi movies. They could be tiny echoes of the same cosmic mysteries Voyager's been uncovering. And here's the thing, you don't need a spaceship to spot them. Some of the most fascinating clues about time's quirks come from ordinary people paying attention to the extraordinary in their own lives. Take Sarah, a nurse from Toronto, who swears her grandmother's antique cuckoo clock chimed 13 times at midnight, on the same night Voyager detected one of its strangest signal echoes. Or Marcus, a taxi driver in Lisbon, who picked up a fare who knew his name, his route, even the song on the radio, only to realize later he'd dreamed the exact same encounter a week prior. Coincidence, maybe, but what if these aren't just flukes? What if they're glimpses of time seems showing, tiny threads fraying at the edges of our perception? This is where you come in. We're turning the comments into a time capsule of your weirdest, most unexplainable moments. Ever had a device glitch in a way that defied logic? Found yourself somewhere you swear you've never been, but every detail felt eerily familiar? Share your story, the stranger, the better. Our favorite submissions will get featured in a follow-up deep dive, complete with expert analysis from physicists and neuroscientists. Who knows, that one weird afternoon might just hold a clue to the bigger puzzle. And because we're all about the science behind the strangeness, here's a pro tip for spotting potential time anomalies in your own life. Keep a glitch journal. Jot down the date, time, and details whenever something feels off, a clock resetting itself, a conversation that loops like a broken record, even a shadow that moves just a beat too slow. Over time, you might start noticing patterns. One viewer, a retired engineer named Hiroshi, tracked his déjà vu episodes for a decade and found they clustered around solar flares, suggesting cosmic weather might tweak our internal clocks. So hit pause and think back. That odd moment you brushed off as a brain hiccup, it might be more than just a fluke. Drop your stories below and let's crowdsource the quirkiest corners of time's behavior. Because sometimes the most groundbreaking discoveries don't come from billion-dollar probes. They start with someone saying, "Hey, this weird thing happened to me once." And having the courage to wonder why. Ever wonder what it takes to turn mind-bending quantum theories into a video that doesn't leave your brain in knots? Behind every polished minute of this story lies a mountain of scrapped scripts, heated whiteboard debates, and enough coffee to fuel a small spacecraft. Let's pull back the curtain. Early script drafts read like a physics textbook crossed with a detective novel, pages dense with equations and wild theories about time loops. Our first challenge, deciding how much quantum weirdness the average viewer could stomach. One team member fought to keep a deep dive into space-time foam, while another argued for replacing it with a simple analogy. Imagine time as a river, but with invisible whirlpools that occasionally spin backward. The compromise, a whiteboard animation that flashed complex math for 2 seconds high, physics nerds, before dissolving into rippling water, a visual handshake between accuracy and accessibility. Then came the animation sketches. Early storyboards depicted Voyager's signals as literal sound waves twisting through a grid representing space-time. But test audiences got stuck on the grid, mistaking it for a computer error. Solution: we swapped it for something more intuitive. a pulsating golden thread knotting to the golden record, unraveling through starry darkness, its kinks and loops mirroring the anomalies. The aha moment came when an intern suggested adding faint, ghostly echoes subtle enough to intrigue, not confuse, but the real drama unfolded over how to explain temporal granularity. One faction wanted a stop-motion sequence of flipping dominoes, each representing a quantum moment. Another pushed for a musical metaphor time as a song where occasional notes stutter like a scratched record. The debate raged until our sound designer dropped a bombshell. Why not both? The final cut layers dominoes falling in sync with a glitching piano melody, creating a multisensory click of understanding. Humanizing the science meant showing our own struggles too. Early voiceover takes included flubbed lines like quantum entanglement, slurred after midnight recording sessions. Outtakes featured the narrator accidentally comparing spacetime to lasagna, layers but not edible. Those bloopers didn't make the final cut, but their spirit did, keeping explanations warm, humble, and relentlessly focused on wonder over jargon. The takeaway: making complex science engaging isn't about dumbing it down. It's about finding the right hooks to pull viewers up. Every animation frame, script tweak, and heated debate served one goal: to make you feel like you're not just learning about time's secrets, but discovering them alongside us. So the next time you watch a science video and think, "I actually get this," remember somewhere, a team is still arguing over dominoes. From the strange whispers of Voyager's signals to the mind-bending possibilities of time's true nature, this journey proves the universe still holds mysteries we're only beginning to unravel. If your curiosity is buzzing after today's deep dive, you're exactly why this channel exists. We live for these moments when science brushes against the unknown, when a single anomaly in decades-old data can rewrite textbooks. And here's the thing: this story isn't over. With new probes launching and labs worldwide chasing these temporal ripples, the next breakthrough could drop any day. Make sure you're here for it. Tap that subscribe button and ring the notification bell, because when the next cosmic puzzle piece clicks into place, you won't want to miss the reveal. Our mission is to bring you these frontiers of discovery, where the line between science and wonder blurs in the most thrilling ways. And if today's voyage through time's secrets left you hungry for more, smash that like button. It lets us know which mysteries to chase next. Before we go, listen closely. That faint, oscillating hum you're hearing, it's Voyager's real-time telemetry signal, beaming back from over 14 billion miles away, a fragile thread connecting us to humanity's farthest reach into the cosmos. Let it linger for a moment. This is the sound of exploration itself, raw, unfiltered, and utterly alive with possibility. As it fades into interstellar silence, remember, the next great discovery might already be whispering to us across the dark. We just have to keep listening. Voyager telemetry signal plays, then slowly